Welcome physics students, this is Mr. Wells and I'm here to give you a quick summary of all the ins and outs of energy. Let's get started. As you know from your prior study of science, there's lots and lots of different types of energy. There's things like thermal energy that's tied to the vibration of molecules. The more they vibrate, the warmer they are, for example. They have a higher temperature, they have more thermal energy. We refer to that thermal energy of vibrating objects as their internal energy. There's heat, which is a transfer of thermal energy. You got chemical energy for bonds and so forth, as you guys have learned about in your chemistry classes. And there's a whole assortment of other types of energy. Now, this year, we're going to be primarily focused on what's called mechanical energy. That's kinetic energy, which is the energy of motion. So when things move, they're going to have kinetic energy. And then also potential energy, which is going to be a stored energy that can then be later converted into kinetic form. So we're primarily focused on just the subset of energy called mechanical. But keep in mind, there's all these other kinds of energy out there. Now you may be thinking to yourself, I've learned in my other classes that energy is always conserved. Isn't that true? Well, even though the total energy in the universe is conserved, the energy of an actual object, a single thing, can change. And the energy can be transferred from one object to another or between different types. So for example, if you look back at this picture with all different types of energy, it's certainly possible, for example, for some kinetic energy for an object to be converted into heat. That happens, for example, when an object slides across a rough surface and friction takes away some of the kinetic energy. It gets turned into heat. Is the total energy conserved? Yes, but it doesn't necessarily remain with the object in the form of kinetic energy. All right, now let's go back to the two types of mechanical energy. We've got kinetic energy, which is the energy of motion, and you calculated that as 1/2 mv squared. This is indicating that the kinetic energy is proportional to the mass. So the more mass you have, the more kinetic energy you have. And it's telling you that the kinetic energy also goes in proportion to the speed squared. That means if you double the speed, you end up with 4 times as much kinetic energy. Now this energy belongs to the object that is moving. The other type of mechanical energy is potential energy, and this is a stored energy. There's a potential energy for every what we refer to as conservative force. So potential energy functions correspond to conservative forces. And a really critical piece here that we're going to talk about in more detail is that your potential energies are really shared energies that are shared within a system. Okay, and we'll come back to that in just a second. So what the heck is a conservative force? A conservative force is a force that when it does work on an object, as the object moves around, that work can be completely undone by simply having the object return to its starting position. So for example, if an object began here at point A and it moved around a point through space and it ended up coming right back to point A, so it started and stopped at exactly the same location, then it may be that as it moved around some work was done, but if by the time it comes back to A, the total work done is 0 by, say, the gravitational force or some other sort of special sort of force, then all of that work essentially got reversed, it got undone. Well, that would be a conservative force. Any force that behaves like this, where every time you move back to where you began, all the work that that force does gets undone, is conservative. And the two types of conservative forces we're going to see for now are going to be gravitational force and the force of a spring. But there's other ones as well. Now let me show you what I mean by the work can be reversed. Let's focus on gravity for a second. So imagine I take an object like a block and I toss it straight up in the air and then I let it fall back down. Let's say that when we toss it up, it's moving at 5 meters per second. Okay, so you toss it up and it's got some kinetic energy. As it rises, gravity is going to take away that kinetic energy and slow the object down. Right? Force of gravity is acting downwards. You know this force of gravity, mg, is going to slow the object, taking away kinetic energy. Now, as the object falls back down, that force of gravity is going to now speed the object back up. As it rises, the work done by gravity was negative because it took away energy. As it falls, the work done by gravity is positive because it's adding energy. But by the time you get back to the original height, your speed is just the same. The kinetic energy is the same for the object at the moment you toss it as when it comes back to that starting height. So all that energy that got transferred by gravity got completely undone. So gravity took some away and then it added it right back when he came back to the same height. So that's what I mean by forces that do reversible work. You come back to the same location, all the work that was originally done by that force gets undone. All right, well, in the prior example, as the object was rising through the air, it loses kinetic energy. And the question is, where did it go? If I push on an object, it makes sense to say that the energy came from me, and that I've transferred energy to the object. But if I have an object that's rising and falling, and gravity is doing the work, it is a very natural question to say, where did that energy go, for example, as it rises? And one answer to this, the one we're going to use, is the concept of stored energy. We say as it rises, the energy was stored as gravitational potential energy, which was then converted back into kinetic energy as the object fell. And that's our basic idea. So potential energy is going to refer to this sort of stored energy, and you can store it when you have one of these conservative forces, and then as that conservative force does work, it will either put more energy into storage, for example, when it does negative work, or when it does positive work, it'll take the energy back out of storage and convert it into kinetic energy. So that's your basic idea. Now, the potential energy for gravity is calculated as mgh. M here is the mass of the object. G is 9.8, and h is the height of the object. And the connection to this to work should be pretty obvious, because mg is the force of gravity, and h here is a measure of essentially how far the object is going to move up or down. It's the height that it starts at. So if it falls, it would have to fall a height h to lose all this potential energy. Okay, now let's talk about mechanical energy of objects versus systems. So there's two types of mechanical energy. There's kinetic and there's potential. But here's the idea. When I'm talking only about a single object, like a car, for example, the only mechanical energy that belongs to that car is its kinetic energy. So right here I'm using E to represent mechanical energy. Now what I'm saying is that for one object, all by its lonesome, its mechanical energy is just its kinetic energy, and that's it. So if its kinetic energy changes, its energy changed. Well, how about if I have a system? And when in the world would I want to have a system anyway? Well, here's the key idea. We talked about the idea of having potential energy, having stored energy. Well, think back to gravitational potential energy. When I threw the object up, as it rose, it would gain potential energy because it's gaining some height. And as it fell, it would lose potential and it would gain kinetic. So we had a scenario, for example, where as this object went up through the air, as it was rising, kinetic was decreasing, potential was increasing. And as it falls back down like this, headed back down, now its kinetic energy was increasing as it speeds up and potential is decreasing. So you notice one goes up, one goes down. Well, what I would like to say is that if I put those two things together, I'm getting the same value, that I'm just moving energy around. In fact, gravity's moving energy around. Gravity's converting the energy from kinetic to potential and vice versa. But that stored energy, that gravitational potential energy, doesn't really belong to the object. It's really shared between the object and the Earth, because gravity is an interaction between the object and the Earth. So for example, if I defined a system as my Earth, say block system, for example, so now I include the Earth and the block, now the total energy is not just the kinetic for the block, but also that shared potential. And that's the basic idea. Anytime I have a conservative force, like gravity, or say a force involving a spring, I can define a system that includes the things that interact via the conservative force. So for gravity, I got to put Earth in there, for example. So the block and Earth, because they interact gravitationally. If I have a block attached to a spring, then my system would be, say, the block-spring system, because they're the things that interact. And if I do that, I can now define the total mechanical energy of the system as both the kinetic energy of the object and the shared potential energy. Well, how in the world do you change the mechanical energy? And the answer is, the way you change energy is via work. Work, by definition, is a transfer of energy through the application of forces applied over some distance. So work is a transfer of energy. How do you calculate it? Well, the work is the force parallel to the motion times the distance that an object moves. And you'll remember that anytime the force is in the direction of motion, so if the force parallel is in the direction of motion, same way that it moves, then in that case, positive work is done, which means you're going to add energy. And that makes sense. If you push the same way something moves, You're going to speed it up. You're going to add some energy. On the other hand, if you push in the opposite direction of the way it moves, then negative work is done, which means that you're removing energy from the object. All right, now let's talk about, again, this idea of work being a change in energy, a transfer in energy, and how to put all this together. This brings us to the concept of the work-energy theorem. So broadly speaking, different types of work, when you add them up, equal changes in different types of energy. So I can just say work equals a change in energy, but this isn't really specific enough. I need to look at specific scenarios to know exactly what this means. Well, what if I'm talking about, say, a single object? Well, for a single object, all of the work that's done on the object corresponds to energy being transferred to it. And all of that energy transfer changes its energy. Keep in mind that the energy for an object is just kinetic. Right? That's all that belongs to the object is its energy in motion. So in this case, the total work on the object equals the change in its total energy, which is just the change in its kinetic. That's called the work-kinetic energy theorem. Well, what happens if I define a system? Something like, for example, that block Earth system when I threw the block up in the air earlier. Well, in that situation, the total energy is the kinetic plus the potential right here. Okay. Now, what will change the total energy? Well, the answer is the work that's done by non-conservative forces. You say, well, why just the non-conservative forces? Why isn't it the total work? And the answer is really important. The idea is that conservative forces like gravity, when they do work, they move energy around between kinetic and potential. For example, when gravity does positive work, it'll take energy that's potential and turn it into kinetic. That's positive conservative work. But when conservative forces like gravity do negative work, they just remove some energy from kinetic and convert it to potential. They go the opposite direction. But the bottom line is conservative forces like gravity and the spring force, all they do when they do work is move the energy around. Kinetic and potential, one goes up, one goes down, but the total stays the same. So in order to change the sum of those two things, I got to have something else doing work, something that isn't conservative. Something like, say, friction or an applied force. Okay? This next diagram should help this make a little more sense to you. So here I've got mechanical energy, and I have the two types, kinetic and potential. And you'll notice that I circled kinetic with red. I have a red box around it. You say, well, why red? Well, up here in the left-hand corner, I'm indicating with my key that red corresponds to just an object. So that might be like the block I tossed up earlier, for example. So, well, notice I've circled all of mechanical energy, both kinetic and potential, with a blue box. Well, that's to indicate that blue refers to the entire system. So remember, when I have a whole system, I can include both kinetic and potential. That's why they're both inside the blue box. But when I'm talking only about an object, its mechanical energy is just the kinetic. That's why it's inside the red box. So red box means mechanical energy of the object, that's just kinetic. Blue box means the mechanical energy of the system, and that's both kinetic and potential. Got it so far? Now here's the idea. When conservative forces like gravity and springs do work, they do what this green arrow is indicating. They move the energy back and forth between kinetic and potential. But they don't make it leave the system. If all I do is make kinetic go up and potential go down, or potential go up and kinetic go down, I don't change the total of the two. Therefore, they don't change the total mechanical energy of a system. Right? Conservative forces don't change the total of kinetic and potential. Now, do they change the total mechanical energy of just an object? Well, since that's just kinetic energy, absolutely they do. When gravity does positive work on an object, it adds kinetic to the object, so it changes that object's mechanical. But in order to get the energy to do the work, it had to take away energy from potential. And so it doesn't change the total mechanical energy of, say, the Earth block system. What about my non-conservative forces? Well, they're represented by this purple line that I'm now going to go back over with, say, some black here. And the idea is, whenever your non-conservative forces do work, they add or remove energy from the entire system, as well as the object. Okay? But remember, conservative forces correspond to certain potential energy functions. There's a gravitational potential energy function. There's going to be a spring potential energy function. They correspond to conservative forces. There is no potential energy for friction, let's say, or an applied force. So when those forces do work, they don't take the energy to and from storage. They just change the total of kinetic plus potential. And if you look at this diagram, you'll notice that both conservative and non-conservative work, both of them together, feed in and out of the kinetic box. That means all work, total work, changes the kinetic energy. By contrast, the only thing that adds or removes anything to this big blue box, the total of kinetic and potential, is the non-conservative work. So work non-conservative, that's what changes the total of kinetic plus potential. And that's the basic idea. All right, so to summarize, we'll say that the mechanical energy is conserved when it doesn't change. And for an object, mechanical energy is going to be conserved if zero total work is done on it. Because all work changes kinetic energy, and the energy of an object alone is its kinetic. Okay? For a system, mechanical energy is conserved, doesn't change, if zero non-conservative work is done. In other words, if only things like gravity or springs do work, then that won't change the total of potential and kinetic, because when those conservative forces do work, they just move the energy around within the system. Okay? Now, even though mechanical energy might change, that doesn't mean the total energy of the whole universe is changing. Remember, there's still a broader conservation principle. For example, when friction, which is not conservative, does work, it may reduce the energy of a system and reduce the kinetic energy of an object, but it just converts it to heat. Still goes somewhere. All right, now let's go back over some scenarios and see whether or not mechanical energy is conserved for objects versus systems. So take the object that I tossed straight up through the air at 5 meters per second, the block. Okay? Is the mechanical energy conserved for just the object as it rises? Well, let's see. The energy for the object is just its kinetic energy. The kinetic energy changes. Therefore, the answer is no. Mechanical energy is not conserved for the object. I can also think about this in terms of the fact that gravity is doing some work. Well, think about the forces acting. The only force is the force of gravity, assuming there's no drag force. And even though that's conservative, it doesn't matter if I'm only focused on the object. Because for an object, all of the work of all types changes its energy. Because all the work changes kinetic. So since gravity does some work, in fact it does negative work as the object rises, takes away some energy, the object's kinetic energy changes and its mechanical energy is not conserved. Well, what about for the object Earth system? Well, now the total mechanical energy for the system includes the kinetic and the potential. Well, gravity may do some work here, but it's a conservative force. When it does work, it just moves around the energy between kinetic and potential. One goes up, one goes down. In other words, there's no work by any non-conservative forces. Because there are no non-conservative forces acting. Only gravity is acting. Consequently, the change in the total mechanical energy of the system is zero. It stays the same. And we would say that the object Earth system has mechanical energy that's conserved. All right, how about a block that slides along a smooth ramp? Smooth means frictionless here. Is the mechanical energy conserved for the block? And then how about the block Earth system? Well, for the block, as it moves down, gravity is going to pull down on it as it slides. The normal force is going to push out at a right angle. You notice that the work done by the normal force here is equal to zero because the normal force is at a right angle to the motion. So it can't do any work. So even though the normal force isn't conservative, it doesn't do any work. So the only work that's done is by gravity, which is conservative. Now, as the object slides and gravity does some positive work, maybe the object goes down like this, it goes faster and faster as gravity does positive work and it adds energy. Because the kinetic energy increases as it moves down, and by the way, it decreases as it slides back up. It speeds up and slows back down. The mechanical energy of the block changes. Keep in mind, for just the block, the mechanical energy is just kinetic, and that changes. And it's changing because there is some work being done. The net work is the work done by gravity, and that's not zero. So there is a change in the mechanical energy. So is the mechanical energy for the block conserved? The answer is no, absolutely not. How about for the block Earth system? Now the answer is yes, because there are no non-conservative forces doing work. The only non-conservative force here is the normal force, and it does no work because it's at a right angle to motion. Therefore, the sum of kinetic plus potential, which is my total mechanical for the system, is constant, or what we would say means conserved. What happens when the object slides down is the kinetic energy, this is when it slides down, it speeds up, so kinetic increases, but the potential decreases. As it slides up, just the opposite happens. The kinetic energy decreases as it slows, but the potential increases because it gains height. Remember, potential for gravity is mgh. The higher you go, the more you have. All right, on we go. How about if the block was sliding along a rough ramp, meaning we have some friction? Well, in this case, the kinetic energy of the block is still going to change. It slides back and forth. And because its kinetic energy changes, we would say that the block's overall energy, which again is just its kinetic, is changing. It's not constant. We've got both friction and gravity doing work. So there's some work being done here, and it's the total work that changes the kinetic energy. Therefore, the block's mechanical energy is not conserved. How about the block-Earth system? Well, now I talk about mechanical energy being both kinetic and potential. I get to include that potential because I put Earth in my system. So, all right, now, is this constant? And the answer is no. So, well, how come it's not conserved? I thought when gravity did work, it moved the energy between kinetic and potential. And the answer is, even though gravity moves the energy back and forth between kinetic and potential and doesn't change the total, I have friction now, and friction is non-conservative. The change in the total energy here is the work non-conservative, and in this case, that means the work that's done by friction. And that work is not equal to zero. Therefore, there is a change in the energy. In fact, it's going to be negative work done by friction. And if there's negative work done, it means the energy of the system is going to get reduced. Over time, this block Earth system is going to lose mechanical energy. How about if I have a cowboy that rides an elevator up at some constant speed? What would happen here? How about mechanical energy for the cowboy? Is it conserved? Well, the key part here is constant speed. Okay. Well, what forces are acting? I got gravity acting down. Okay. I've got the normal force of the elevator upwards. But because it's a constant speed, we know that the normal force and gravity are equal to each other. All forces have to be balanced. Now, is gravity doing work as the cowboy rises? The answer is yes. Because gravity's down and the motion is up, he's riding the elevator up, gravity does some negative work. How about the normal force? Does it do work? The answer is yes. It's up and the cowboy moves up, it's positive. But the key point is, because the speed is constant, the kinetic energy, 1/2 mv squared, is constant. And because the energy for just the cowboy is just his kinetic, that's constant, and therefore we can say yes, the total mechanical energy of the cowboy is conserved here. This is an interesting one because there is work being done, but the total work is zero because normal and gravity do offsetting amounts of work. So the energy is conserved, even though some work was being done. How about the cowboy Earth system? Well, now my total energy is kinetic plus potential. And I can reason out that because the speed doesn't change, the kinetic itself always stays the same. But the higher the cowboy goes, the more potential you have. So the potential's got to be increasing the higher he goes. Remember, U is mgh. So since potential is going up and the kinetic staying the same, the total must increase. So does the cowboy Earth system have conserved energy? The answer is no, it does not. The energy actually increases. So how do I explain that in terms of work? Well, the change in the mechanical energy is the work done by the non-conservative forces. And here, that's the normal force. That's the non-conservative force. And we already indicated earlier that that was positive work. That means some energy got added to the system, and that explains why the total mechanical energy goes up. All right, we're going to talk about springs, but before we do that, let me show you a couple of simulations. This is one of a skateboarder who's riding a skateboard on a ramp, and this is a lot like the block that was sliding along. If I put this skateboard up here, look at the bar graph to the left. The blue is the potential energy. The green, which you can't see right now because it's zero, is the kinetic energy. There's a red for thermal energy, and there's the yellow, which is the total of all those things. Now, when I let go, this potential energy is going to be converted to kinetic energy as gravity does work. So gravity starts doing some work, and he gains kinetic and loses potential, but as he goes back up, he gets the potential back. Okay? You'll see that kinetic goes up, potential goes down, and vice versa. If I slow this down, you can really see it happening. There, kinetic's rising as he speeds up. Now, kinetic's decreasing, potential is increasing. And you'll notice that that yellow bar never changes. The total of all the energies, kinetic, potential, and thermal, are staying the same. In fact, there is no thermal energy right now. The thermal energy they're talking about would be heat. That would be produced if there was some friction. Where friction takes away energy and produces heat. It turns it into heat. But right now, I got no friction. Well, what happens if I add friction? Well, if I add a little friction here, now notice that this red bar is getting bigger and bigger. That means we're losing more and more energy from kinetic potential. It's becoming thermal. If I just throw away that thermal energy, so you can see what happens, the yellow is now the total of kinetic potential, and that's getting smaller and smaller and smaller over time. Every time I look at just kinetic potential, which is now the yellow, you'll see it gets smaller and smaller over time. Here, I'll reset this, and you can watch again. So I'm going to keep getting rid of the thermal piece, so all you see is the total changing. See the yellow getting smaller and smaller? That's because friction keeps taking away energy. And that's the idea. All right, on we go. When a spring is compressed or stretched, energy is stored. The spring then has the potential to do work on an object and convert that stored energy back to kinetic energy. The way you calculate the energy stored in a spring is with the formula 1/2 kx squared. K is the spring force constant in newtons per meter. It tells you how tight the spring is. So if the spring constant is 100 newtons per meter, it means it would take 100 newtons of force to keep the spring stretched at 100 meters of stretch. So the more you stretch it, the more the spring is going to pull back. But K is just telling you right now, if you want to think about it conceptually, how tight the spring is. Bigger K means tighter spring. X here is how far you stretch or compress the spring. So what this is saying is, if you double the amount of the compression or stretch, because the potential goes as x squared, you'd quadruple the energy stored to double x. Now, let me show you why springs make sense as conservative forces. Watch this simulation. I'm going to hang a mass here, and I'm going to lift up, and I'll let it move back and forth. And you'll notice as it moves back and forth, it just oscillates back and forth, back and forth. Okay? Let me increase the stiffness of the spring so that it won't move quite as much. Okay? And it's going to move back and forth. You notice as it goes back and forth, in theory, if there's no friction, it just repeats forever. So this seems to be completely reversible. It makes sense that when things are completely reversible and they just keep repeating, that there should be a conservation principle, and I should have some sort of potential energy at work. Now, if you look at the bar chart here, the green is the kinetic energy. The dark blue is gravitational potential, and the light blue is the spring potential. And you notice they all keep changing. Now, let me make it move a little bit less. There we go. I'll move a little bit less. The total energy is this last column. You notice the total is never changing. All that's changing is how much of it is the green, kinetic, and how much of it is the dark blue, gravitational potential, and how much of it is the light blue. The higher the item goes, the more energy stored in gravitational potential. The lower it goes, the less is stored in gravitational potential. The more the spring stretches and compresses, the more that's stored in elastic potential energy in the spring. And of course, the faster it goes, the more you have is kinetic. But you can see there's definitely some sort of conservation principle because it just keeps repeating. Okay. Now let's say that I take a spring and I compress it, as you see in this picture. Okay, so this very first picture, I've compressed a spring by an amount A. The idea is I've stored potential energy. And you can tell right here there's a lot of energy in potential, but the kinetic is 0. Okay? I then let go. The spring, as it pushes out on the object to try to keep from being compressed, tries to uncompress, it speeds up the object. And when the object gets back to that natural length for the spring, now I have a maximum amount of kinetic energy. Everything's in kinetic. And potential is now 0. As the object keeps stretching the spring out, it'll begin to slow down as the spring pulls back. The spring's now pulling back this way to try to slow it. And the idea is now, as you stretch the spring again, you again store energy in the spring. And the kinetic is back to 0 again. So what happens when I attach a mass to a spring is, every time the spring gets more compressed or more stretched, more energy gets stored in it. And essentially the spring, being conservative force, just moves the energy around from potential to kinetic. And if I have a vertical spring like I showed you a minute ago, it's a little more complicated because there's also gravitational potential. But nevertheless, I have a scenario where energy just gets moved around between stored energy and kinetic energy. Now, for that block that's attached to, say, a spring, say the horizontal spring we just saw a minute ago, is energy conserved, assuming there's no friction? Well, remember again that for a block, the energy is just the kinetic. That's all it is. Well, the kinetic energy changed as the object moved back and forth because the spring was doing some work. It was pulling on the object and changing the kinetic. Therefore, since work was being done by the spring, and that wasn't a zero amount, the kinetic changed, the energy changed. So no, the block's mechanical energy was not conserved. Well, how about the block spring system? If I have potential energy for the spring, it's got to be shared between the spring and whatever the spring interacts with. That's the block here. So I can now create a system. If I do a block spring system, my total mechanical energy is now the kinetic of the block plus the energy stored in the spring. In this case, when the spring does work, it just moves the energy back and forth between stored energy and kinetic energy. Now, only non-conservative forces would change the total energy of my system. And I don't have any of those. The only thing that does any work here is the spring. Therefore, since there's no non-conservative work, the total mechanical energy is conserved. The answer is yes. All right, let's talk about power for a second, then we're done. Power is the rate of energy transfer per time. It tells you how quickly, essentially, energy is being transferred or work is being done. Imagine, for example, that you hop in, you got a van maybe, and you got a Ferrari. And you imagine if you hop in each of them and you hit the accelerator, you can accelerate them both up to a very high, a large kinetic energy. But in other words, where they're moving very, very fast. But the engine of say, a Ferrari is much higher power, which means it can speed the car up a lot faster. It can get its energy transferred to it much, much more quickly. Well, that's the idea of power. The more quickly you transfer energy, the greater the rate of power. The more slowly you transfer the energy, the lesser the rate of power. The formulas go like this. And the way you calculate the average power, which by the way is measured in watts, a watt's a joule per second. The way you calculate the average power is by taking the work done divided by the time that the work was done in, or equivalently the energy transferred over the time it took to transfer it. So for example, if the work done was 50 joules and the time that it took to transfer it was 10 seconds, the average power would be 5 watts. On the other hand, if the work had been 50 joules, you transferred just as much energy, but now it took you much longer. Maybe it took you 50 seconds to do it. Now the average power, 50 over 50, would be only 1 watt. So again, the more time it takes to transfer that energy, the less the power is going to be. Now you can also calculate the power directly from forces. And the way you do it is by saying that the power is the force parallel to the motion times the velocity. And this gives you an instantaneous rate. If I know how much force is parallel right now and how fast things are moving right now, I can multiply those things and get the power, the rate that energy is being transferred at right now. All right, well, this does it for the video. I hope you enjoyed it. I hope you learned a lot. And we will see you in class. Bye-bye.